Okay, I'm just going to get into it today, I think, because we spent a lot of time on a homework problem last time. But there's one thing. It was number 5, right, Tracy? It was in the set stresses in objects loaded like stress elements. There's got to be a simpler way to write that name. The size of the class just increased by like 25%. So number 5, it was a big truss, and it asked for the maximum shear stress in the elements, and so you need to know a cross-sectional area. So let's just choose one. Let's say cross-sectional area of the members is 0.001 meters squared. Okay. So we've been talking about, yes?
Whenever you just give us the cross-sectional area, do we assume that it's a circular beam or like a square?
If I just give this, then it's because it doesn't matter what the shape is, but I guess, so this would be true whether it was rectangular or circular or $ shaped or whatever.
Okay. Well, when we're given that, what's our distance, L, for the...
Yeah, that's a good question. That is a really good question.
That's
Yep.
the only, I had the same question.
I see. Yeah, that's a good point. Sure, circular.
Okay.
Yep. Okay, so we've been doing internal loads. And we've done it with point loads. We've done it with point external loads, but we have to talk about when the external loads are distributed loads. Okay, so distributed loads. And I think everybody's seen this in statics. But to do calculations with distributed loads, you have to do two things. You have to first calculate the total force applied by the distributed load. And second, you need to calculate where that force would be applied where that point force has to be applied to make this an equipolant system. Something that's going to come up now in using distributed loads for internal loads is you have to know at what stage is it okay to replace a distributed load with a point load? If you do it at the wrong time, you're going to get the wrong answers. So when can you do this? When can you make this switch to a point load? And you can do it after you've chosen what body to isolate. If you first treat the distributed load as a point force and then choose the body to isolate, choose the part of the beam, for example, to isolate, you get the wrong answers. So you have to make this switch after you choose the body to isolate. Body, or for internal loads, or the part of the body. The total force is the area under the distributed load shape and the point of force application, the point where that force is applied, is the centroid of that distributed load shape. So let me give you, we don't need much here. Actually, I'm just going to give you one, the centroid for one shape that we're going to use all the time. And I'll talk about symmetry. And then if you need any other ones, there's a PDF on D2L that gives you all the centroids. So centroids. The first thing you have to know is the centroid of a shape lies along any line of symmetry. No. Okay, I guess I will. And if it lies along any line of symmetry, that means if you can find two lines of symmetry, this is if we're in 2 dimensions, then the centroid is at the intersection of those 2 lines. Okay, so rectangles, circles, that's supposed to be like an ellipse. You have a line of symmetry there, a line of symmetry there, so the centroid is where it crosses. A circle, you have infinitely many lines of symmetry, but they all cross at the centroid. An ellipse has these. And then the other shape we're going to use all the time is a right triangle. In 3D, we're not, in this class, we're not going to use 3D centroids, but what's the equivalent of the two lines of symmetry thing in 3D?
3 lines of symmetry.
Close.
What are they
But
gonna
3, yep, it's not. So in 3 planes of symmetry. Yeah. Because 3 lines in 3D don't necessarily intersect anymore. But 3 planes do intersect and they make a point. And so any plane of symmetry you can find, the centroid has to lie on that plane. Okay, so the last one, we'll use this one all the time, is a right triangle. So if you have a right triangle with a horizontal length B and a vertical length H, the centroid is here. Where this distance is B over 3, and this distance is H over 3. Okay, so let me first do an example before we get into internal loads, and then I'll talk about how to extend that to internal loads. So let's say that we have all right, so let's say we have a beam that's connected to the ground with a pin joint at the right end and a roller at the middle. Let's say this is 0.5 meters and this is 0.5 meters. And the only external load besides those reactions is a distributed load that's a right triangular shape. And let's say that this has a height of 10,000 newtons per meter. And we just want to calculate those reactions. Okay, so free body diagram. At the right end, that pin joint applies a full force vector. I'll call that RB, that's a vector. The roller applies an upward force. I'll call that RA. And then we have the distributed load. And now we've chosen the body to isolate. So now it's okay to use those rules of distributed loads to represent this as a point force. So I'll redraw this free body diagram. RB, RA. The total force is the area, which is, so it's this triangular shape has a length of 1 meter, a height of 10,000. So 1 times 10,000 divided by 2. So we have a total force of 5,000. And the location of the centroid is a third of the way from the left end. And it's also a third of the way up. But remember, it doesn't matter where you move a force along its line of action, so we don't care about vertically where, we can vertically put it wherever we want. So the key thing is that it's a third of the way from the left end toward the right end. So right here, and the total force is 5,000. And that means that this distance is 1/3. Any questions about that one?
Why is that force down 5,000?
It's the area of the triangle.
Oh.
The triangle has a height of 10,000, a width of 1, so just take the area, and that's what you're always going to do with distributed loads. So Newton's second law says 0, negative 5,000 plus 0 RA plus RB X and Y components is equal to zeros. And the moment equation, let's choose an about point. Let's choose it over at the right end point. So then the force RB doesn't produce any moment, if that's the about point. RA, what's the moment arm for RA? 0.5. Yep, 0.5. RA, and then would that cause a clockwise or counterclockwise rotation around the about point?
Where's the about point again?
The red. Clockwise, so this is negative. And then the 5,000, what's its moment arm?
2/3.
Yeah, so 2/3, and it's counterclockwise. It's counterclockwise, so it's positive 0.667 times 5,000 is equal to 0. So that says 0.5 RA is equal to 3,333, and so on. And therefore, RA is equal to 6,666, and so on. And then plug that back into the first set of equations, and you get RB is equal to 0, negative 1666.6 repeating. Any questions about that? Okay, so now we're going to do this with internal loads. It's the same idea with internal loads. Things change a little bit when your cut happens inside the distributed load. So the only time it's different from above is when the cut occurs inside the distributed load. In that case, you can do two steps. So first, represent the distributed load height at any x value by the function q of x. And actually, this will be a downward distributed load, which is, I think, what every single calculation we're going to do is. So that means that if you get a positive value of this function q of x, that's a downward force, like a weight. And then second, use that function q of x to represent the height of the distributed load at the cut, which, remember, is position x. So you can just directly use this function. Okay, so let me do an example. Let's say we have a cantilever beam with a triangular distributed load. Let's say the length of this beam is 2 meters. And the height of the distributed load at the right side is 4,000 newtons per meter. What are the internal loads? Let's see. Okay, so normally the first step in internal load calculation is calculating the external loads. I mentioned this once before. If you happen to have a cantilever beam where the only unknown reactions are applied all the way at the right, remember, those don't come up ever in internal load calculation, so you can just skip this step if you want. So let's skip that and just go right to the internal loads. The external loads at the wall won't affect the problem. So I'm going to skip it. Okay, so how many places are there where the subfunctions can change? There's the two endpoints, so your starting is always 2. Between the two endpoints, are there any points where there are point loads or where the function representing the distributed load changes? Nope, it's all represented by this one, it's all this triangular distributed load. So we just have 2 of these points where the subfunctions can change. So n equals 2, and we just need 1 cut. So cut 1 represents all x values between 0 and 2. And we're going to just cut some arbitrary distance in here. So this is the piece that we're isolating. So all this stuff is going on outside of what we care about. But all we care about is the part of the distributed load acting on this black isolated piece. So out here, the height of this triangle is 4,000 newtons per meter. But the part that we care about has some height that depends on x, and x is arbitrary. And then we have these internal loads. I'm going to leave off the internal torque on this because nothing is producing any moments about the x-axis. And now that we've chosen the body to isolate, this black piece is what we're isolating. Now we can represent that distributed load as a point force. The first thing we have to do is figure out a function q of x that represents this distributed load. So how are we going to do that? What's a function q of x that represents this line is what we're looking for. Well, we know it's a line. So mx plus b. When x is equal to 0, what's the height of this distributed load? X equals 0 is on the left side. So when x is equal to 0 on the left side, this distributed load is 0. Follow what I'm talking about there?
Yes.
So this goes away. And now we have to represent the slope of this line.
2,000.
Yeah, so the slope is the rise over run. It rises 4,000 over a distance of 2. So we have 4,000 over 2 times x. So y, which is what we're calling q of x, is equal to 2,000x. And since in our cut, x represents the right side of this beam, x always represents the right side, this is x, and therefore this height is 2,000x. Okay, so now we want to represent this chunk of this triangular distributed load as a point force. What we have is a triangle with a height of 2,000x and a width of x. So what's the area? Have you guys had areas of triangles? A lot of times that's like in 10th grade. Okay, good. 1,000x squared. And then what's the distance from the left end of this triangle to the centroid? 2/3, yep. So 2x over 3. Yep, exactly. And so now we can rewrite this free body diagram. We have the internal loads. And we have now a point force of 1,000x squared acting at 2x over 3 from the left end. So Newton's second law says 0, negative 1,000x squared plus t negative v is equal to zeros. So t equals 0, and v equals negative 1,000 x squared. And then the moment equation, we're taking the moments about the left endpoint. We always do that on all these internal loads calculations. You can put it anywhere, but this will make the calculation simpler. What's the moment arm of that 1,000 x squared?
2x over 3.
Yep, so 2x over 3 is the moment arm. The force is 1,000 x squared, and is that clockwise or counterclockwise? Clockwise, so that's negative. And then plus m minus Vx is equal to 0. So m is equal to 666.6 repeating x cubed plus Vx. And if you substitute in Vx, you get 333.3 repeating x cubed. Excuse me. Any questions about that? So I think if you're doing this for the first time, or especially, a lot of you have done this before, but not for a while, I think the best way to go at first is just write out all the steps. Draw out a free body diagram with the distributed load, go from that to calculating the area, then write down the free body diagram with the point force. It feels like a lot of extra steps, but it'll keep you from forgetting anything until it gets sort of fluid again. Yep.
Is it at negative 3333?
Yes, thank you.
I keep showing you.
You're right about that. It has to be. Okay. One place that distributed loads are going to come up with internal loads is weights. So when we're calculating internal loads, weights always have to be treated as a distributed load. We didn't have to do that before because what we did when we were using weights to calculate external loads is we chose our body. That was the body that we were given the weight for. And then after we'd chosen the body, it was sort of already done for us, then we treated the weight as a point force. But now we just have to be careful. Weight is always a distributed load. But now we just have to be careful because we're going to take out a chunk of that body and isolate it. And we can't treat the distributed load of the weight as a point force until after we've isolated that piece. So let me just, I think an example is the easiest way to do this. So let's do a cantilever beam connected at the right again, because we're lazy and we don't like to compute external loads. So let's say this is, no, let's say that's 2 meters long again. and let's say that the mass of this beam is 100 kilograms. What are the internal loads in the beam? So how many places are there where the subfunctions can change? There's the two endpoints, and then between the two endpoints, are there any point loads or any places where the distributed load function will change? The weight is just a uniform distributed load. We can just get that by taking the weight divided by the length, and that's just going to be constant over the whole thing. So n equals 2, just the endpoints, and that says that we're just going to need one cut. Okay, so a free body diagram of our cut. Let me write that as, okay, so our first cut, our only cut, is valid for x between 0 and 2. There's this stuff going on at the wall over here that we don't care about. And there's a distributed load representing the weight that we don't care about. And then the black is the part that we're isolating. So there's the internal loads. And then this distributed load representing the weight. If it's 100 kilograms, then the weight is that times 9.81. So 981 divided by the length of 2. So we get a distributed load of 490.5 newtons per meter. And this distance is x. Okay, so the first step is to come up with that function q that tells us the height of that distributed load at any x value. In this case, this value is constant. So q of x is a constant function just equal to 490.5. And now that we've chosen the body to isolate, we want to represent that distributed load as a point force. The shape that we're dealing with is a rectangle. It has a height of 490.5 and a width of x. So what's the area of that rectangle? You guys done rectangles?
49.5x.
Yep, good. And then the centroid of a rectangle is, it's just going to be x over 2 from either end. Okay, so we have a total force of 490.5x. Where this distance is x over 2. And then we have the internal loads. So Newton's second law says 0, negative 490.5x plus t negative v is equal to zeros. So t is 0, v is negative 490.5x. And then the moment equation, our about point is at the left. So what's the moment arm of 490.5x? X over 2 times 490.5x. And then is that clockwise or counterclockwise? Clockwise, yep. So negative plus m minus Vx is equal to 0. So m is equal to 245.25. I left off an x in this function. So in that first term, that should have been 490.5x is the force. So m is equal to 245.25x squared plus Vx. And so that's equal to negative 245.25x squared. Yep.
Oh, never mind, I just saw your about point.
Okay. Yeah.
What are you referring to with v sub x?
That's not v sub x, that's v times x, because
Oh,
the moment arm of v is x. And so you just take that, the v that we already solved for, and multiply it by x. Yep. Any other questions? Okay, so there are 6 relationships between, well, really there's 2 relationships between these internal load variables, and then some other things that we can look for. And I use those just to troubleshoot my answer at the end. You can also work this problem the other way and use these relationships as a way to solve the problem. Different teachers teach this stuff in different ways. So here are the relationships, and I just call these the 6 checks on our internal load calculations, but I'll try to sort of point out how you could use it to solve the problem in the first place if you wanted. My experience, by the way, is that the 2 are the same. Like as far as time, how long it takes or whatever, there's really no advantage to one way or the other. But okay, here are the 6 checks on your internal load answers. Bless you. The first one is at every point dm dx has to be equal to v. Okay, so let's look at the 2 examples we did. Each of these only have one cut, so we only have to check this in one place. But dm dx is equal to negative 490.5x, so it works in that one. The example before, dm dx is equal to negative 1,000x squared, so it works in that one. And so a lot of times if you make a mistake, if you do this check and the other ones that I'm going to talk about, you can find errors that you made. The second is that at every point, dv dx is equal to negative q, q at that x value. So let's check that. For the example we just did, q is equal to 490.5. Take dv dx, you get negative 490.5. So negative dv dx is positive 490.5, so that works. The example before, q was equal to 2000x. dv dx is negative 2000x. Negative dv dx is positive 2000x, so it works. Okay. The third one. Now these two are true for every point, okay? The last four are only true at the endpoints. But the first one says t equals 0 if and only if there's no horizontal point force at that endpoint. What if I took that call and that was like some really embarrassing, like, medical call? You know? Never mind.
Embarrassing for who?
For all of us. It would be embarrassing for all of us. I assure you. Okay. The fourth one, okay, well, let's check the last two examples for this one. We can only, for these last four checks, since we were lazy and we didn't calculate the external loads at the right endpoint, we can only do these checks at the left endpoint. But if we had calculated the external loads at that cantilever at the wall, we could do this check at both endpoints. Okay, but let's do it at the left. So in the example we just did, are there any point loads, horizontal point forces acting at the left endpoint? No, there's a distributed load, but a distributed load is not a point force. So that says that the internal tension needs to be equal to 0 at the left endpoint. What am I doing? So go to t, and actually t is equal to 0 over the whole thing. So that one checks out. The next check at any endpoint v is equal to 0 if and only if, what do you think? Yep, no vertical point force at that endpoint. Okay, so is there a vertical point force at the left end in this problem? No, not at the left.
Point force, no.
Right, no point force. And so we'll go to the function v. The left endpoint is represented by x equals 0. So plug in 0 here. You get a shear force that's equal to 0. And so that checks out. The fifth one. These are all very similar, but we're just going through each of these values at the endpoints. At an endpoint, m is equal to 0 if and only if. What do you think this one is?
There's no moment.
That's right. No point couple about the z-axis at that endpoint. Is there a point couple about the left endpoint in this problem? Nope. So go to the function m, plug in 0 for x, and you get that m is equal to 0, so that one works. We care about it, but we can't check it because we didn't calculate those external loads. Remember, we skipped that due to laziness, mostly your laziness. And so, but if we'd calculated those, then we would check both endpoints. And then the last one, at any endpoint, fancy T, the torque is equal to 0 if and only if there's no point couple about the x-axis at that endpoint. Well, we didn't have any we didn't have any moments about x in the whole problem, so our torque was equal to 0. There was no torque at that point, so that one checks out. Okay, so you can imagine, not the endpoint ones really, well, I suppose, but with these two derivative relationships, you could imagine using Newton's second law, calculating the shear force as a function of x, and then integrating that to come up with the bending moment. And you can do that, but you have to be careful at the boundaries of distributed loads and things, because if you have point couples, it creates a jump in this graph. So anyways, you have to be a little bit careful about it, and it works fine, but it doesn't end up saving any time. It doesn't take any more time either. But I don't know. If you ever have extra time, try doing a problem that way and see if you can make sense out of it. Anybody have any questions about this? All right. Let's take a 10-minute break, come back at 10 after, and I'll just go through another example problem or two. Hi. Oh, no.
How are you?
Yeah, because total weight, because the length is 2, and that distributed load is like how much force per length. You know what I mean? So you're just taking the total weight of the thing and dividing it by the length of the thing. Yeah, because that's just telling you the force applied for every meter at that distributed load. So, yep. Hi.
Question about the centroid.
Yeah.
So
centroid is 0.5 over from either side of that little square, right? But first you have to go 3 over to get to the left end of that square.
So didn't we treat like every shape by itself? Like
Nope, you have to do it all in terms of that coordinate system. So, I mean, like basically you're just, so there's your shape, there's your centroid, and you're just trying to come up with the coordinates of that centroid in this
so
coordinate
here's like
system.
0, 0.
Yeah,
Okay.
exactly.
Can I get my quiz back?
Yeah.
Okay. I had a question on part E.
Mhm.
It says give a stress tensor containing the maximum shear stress. I'm not, like I saw the values that you had on your solutions, but I'm not sure how you did it. I'm guessing it's a rotational
Yeah.
and then multiplied by.
So you're finding the principal stress tensor and then rotating by 45 degrees about the middle axis.
Yeah, so it's just multiplied by my midpoint.
So multiply, take the, so, find that rotation matrix.
Yep.
That rotates 45 degrees about the middle axis, and then take that times the principal stress tensor times Q transpose, and that gives you a stress tensor that has the max shear in it.
Okay.
Oh, whoops. And so after we do this one more example, nope. I'm going to talk about using rotation matrices to do internal load calculations for members in structures. Okay, so let's say that we have this thing. Well, let's put the pin joint at the middle. And a roller there. And let's say there's a distributed load applied to, no, not that half, applied over here. And let's say this distributed load is 1,000 newtons per meter, and this is 0.1 meters, and this is 0.1 meters. And we want to calculate the internal loads. Let's do a torque in this one too. Let's say there's a horizontal point force applied on this side of 200 newtons, and let's say there's a torque this way on the other end of 100 Newton meters. All right, the first thing we have to do is calculate the external loads. So a free body diagram of the whole thing. At the middle, that pin joint produces a full force vector. I'll call that RA. And the roller at the right end applies a force down. I'll call that RB. And then there's the 200 Newton force over here. The couple about the x-axis over here. And then what's the total point force applied by this distributed load on the left? That's a rectangular distributed load. So height of 1,000, width of 0.1, so that's 100. And this distance is half of this, so 0.05. So question? So Newton's second law says 0, negative 100 plus RAX, RAY plus 0, negative RB plus 200, 0 is equal to zeros. And the moment equation, let's calculate that about the center. Oh, we have to split this up into an x and y component. So first let's do it for z. What's the moment arm of this 100? The only 100.
There's an 100.
Oh, yeah, you're right. The downward.
0.05 meters, sir.
Yes, thank you. 0.05 times 100. And is that clockwise or counterclockwise? Counter, yep. And then the RB, what's its moment arm? I'll just write it up here while you think. Yeah, 0.1. And is that clockwise or counterclockwise?
Clockwise.
Clockwise, so that's minus, yep. And then what about the 200? Does that produce a moment about z?
That'd be a negative.
Nope, that's right, because the line of action goes right through the about point. So RB is equal to 50? And RA then, plug it back into the top stuff, is equal to negative 200 and positive 50. No, 150, right? Yeah. Any questions about that? And then we have to deal with the torque, too. So the moment equation about the x-axis, that's pointing in the negative x direction. So we have negative 100. And I didn't put this. This is really egregious, but I did not put this in the free body diagram, but I'm going to do it now and pretend like it was there all along. Okay, so this pin joint here is where we have, I'll call that TA. That provides a couple that keeps this from rotating about the x-axis. With me? Vadim, you with me? Huh? Yeah, that's what I thought. Okay. So negative 100 plus TA is equal to 0. Any questions about that? Okay, so TA is equal to 100. And those are all the external loads. All right, so now, this is an easy mistake to make. If we looked at the free body diagram that I just did of the whole thing to figure out how many places there are that the subfunctions will change, it's very likely that we would make a mistake about that, because it looks like there are the two endpoints, a point force here, and and some point loads at the middle, right? So that looks like 1, 2, 3, 4 points, n equals 4, 3 cuts, right? But that's not true. This 100 is a mathematical thing for our benefit. That's not a real point force. So really what you want to do is look back at the original thing. You have the two endpoints. You have point stuff happening at the pin. And then the only other stuff that matters is where the distributed load functions change. And they change at the endpoint, which we've already counted, and at the pin joint, which we've already counted. So really n is equal to 3 on this, and we only need 2 cuts. Okay? Okay, so n is equal to 3. There's 2 cuts. The first cut is for x values between 0 and 0.1. So we're making a cut somewhere in here, which means we're only dealing with part of this distributed load. And then we have the internal loads, T, V, M, and fancy T. And we have a couple of, what was that, 200? 100? 100. Any questions about that? And this distributed load has a value of 1,000. So now that we've chosen the body to isolate, we can treat that as a point force. So I'll redraw that. So we have the 100 over here. The internal load's over here. And representing this distributed load as a point force, this whole thing has a length of x. So what's the magnitude of that point force? It's the area of that rectangle.
100x.
This is the one, it's 1,000x. Yep, right. So 1,000x acting down, and that's right at the midpoint. So this distance is x over 2. So Newton's second law says 0, negative 1,000x plus t negative v is equal to zeros. So t is equal to 0 and v is equal to negative 1,000x. And now we'll do the moment equation about the z-axis. The moment arm for the 1,000x is x over 2. Is that clockwise or counterclockwise? There's the about point. That's clockwise, so yeah, negative x over 2 times 1,000x. And then plus m minus vx is equal to 0. So m is equal to 500x squared plus vx, so that's negative 500x squared. And now about the x-axis, we have the negative 100 and fancy t. And so fancy t is equal to positive 100. Any questions about that cut? Yep.
When we're looking at these numbers or equations, if we create graphs for them, how would we interpret those graphs? Like, for example, the m
Mhm.
graph is just going to be an outside of m parabola.
Yeah.
So then it just reaches the maximum and goes back down. So does that mean that as you approach some point on the bar, you get the moment as the most moment you can get, and then, or how would you interpret that graph?
Well, yeah, if, let's see, that would be equal to, it would look something like this, where I think the maximum value would be negative 5, right? So that just says that as you approach that midpoint, your bending moment is getting bigger and bigger. So physically, that means you're getting more concerned about the material breaking as you get closer to that midpoint. As far as like how to make that graph, put it in one of a million programs that graph stuff for you and never think about it again. You know what I mean?
Okay, sure.
Okay. Okay, now the second cut. So cut 2 is for x values between 0.1 and 0.2. So now we're looking at a piece like this. We're including the stuff happening at the pin. What were those values? So negative 200, 150. And then there's also the torque. What was the torque value at the pin?
Negative 100 or something? 100.
100. Okay, 100. And we're including this whole distributed load now, which means we can just treat it the way we did when we calculated those external loads. So that just has a value of 100 acting down. And the location is 0.05 from the left end point. And we have the torque of 100, and then we have the internal loads. So Newton's second law says 0, negative 100, plus negative 200, 150, plus t negative v is equal to zeros. So t is equal to 200. V is equal to 50. And then the moment equation about the z-axis. We have 100 times 0.05, and that's a clockwise moment, so -5. Then the upward force of 150 has a moment arm of 0.01. That would produce a counterclockwise moment, so 0.1 times force of 150 plus m minus Vx equals 0. So m is equal to -10 plus Vx. So that's -10 plus 50x. And then the last thing we have to do is the moments about the x-axis. So now we have the -100 plus the +100 plus fancy t is equal to 0. So fancy t is equal to 0. And now you can do all those checks to make sure that you didn't make any dumb mistakes that you can find easily. dm dx is equal to v, so that's good on the second half. On the first half, dm dx is equal to v, so that one works. Then check that dv dx equals -q. On cut 2, what's the value of q equal to? So remember, if you look at the original picture, if we're doing a cutout here past where the distributed load is, q is just equal to 0, right? So anytime your cut isn't inside a distributed load, that's just saying your shear force has to be a constant. So go to cut 2, look at the shear force, it's a constant, so that works. What about cut 1? The Q value is 1,000, it's constant. Negative dV dx is 1,000, so that one works. Any questions about that? I feel it too. I feel it. What should we do about it? There's still 15 minutes of class, and we still have 6 more topics to get through today.
Let's keep going.
Let's go. Let's go. Let's go. All right, so what about internal loads and structures, you ask?
Professor?
Yes.
What about internal loads and structures?
I'm glad you asked, Bob. Okay, so internal loads and structures. The only thing that's different here is the members are not horizontal. And so we have to do something to represent, we have to change the coordinate system so that the member's long axis is along our new x-axis. Then we can do everything the same as we did before. So here's an example. I'm just going to do this with an example, I think. Okay, so there's a wall. It's supposed to be vertical. And here's a cantilever beam at an angle of 30 degrees from the horizontal. Let's say the length of this beam is 0.2 meters. And let's say we have a downward force of 6,000 newtons. And we want to figure out the internal loads in this beam. Okay, well, free body diagram. We have the downward force of 6,000. We're neglecting the weight of the beam. It's negligible compared to all these other forces. And then the fixed joint at the left is a full force vector. I'll call that RA. And a couple, I'll call that MA. So Newton's second law says RAX, RAY plus 0, negative 6,000 is equal to 0. So RA is equal to 0, positive 6,000. And then the moment equation says MA, and then what's the moment produced here? Well, you could write out the pancake table for this and calculate that all with vectors, or you could just recognize that, just do it with the trigonometry. This angle's 30 degrees. This length is 0.2. So the moment arm is 0.2 times the cosine of 30, which is 0.1732 times the force of 6,000, and I'm calculating these moments around the left end point. So would that produce a clockwise or counterclockwise moment? Clockwise, so negative is equal to 0. And so MA is equal to 1,039.23. Okay, so the thing is, we don't care that that beam isn't horizontal. What we care about is that our coordinate system isn't lined up with the beam. Okay, so it's not really a matter of rotating the beam to be horizontal. It's a matter of taking the coordinate system that is originally like this and re-expressing everything in a coordinate system like this, where this angle's 30 degrees. And that is very easy to do with rotation matrices. So which way are you rotating the coordinate system, and about what axis to go from here to here? That's right. So theta is equal to negative 30 degrees about z. And so the rotation matrix is just cosine of negative 30, sine of negative 30, negative sine of negative 30, cosine of negative 30, and then like that. And so you get 0.866, negative 0.50, positive 0.5, 0.866, 0, 0, 0, 1. And now we're just going to go through all those loads and multiply the load vector by this rotation matrix to represent it in the new coordinate system. We could do it with the couples, but those are about the z-axis only, and so rotating things about the z-axis that only have a z component doesn't change it, you know? So, okay. What do we have to rotate? This force RA. So we have 0.866, negative 0.50, positive 0.5, positive 0.866, 0, 0, 0, 1. And we're multiplying it by our RA vector of 0, 6,000, and we did it all in 2D. All the Z stuff on these forces is all 0, so like that. And you get a value that's equal to negative 3,000, $5196.150. And now we need that 6,000 Newton force. Well, the external, the one on the right end, okay, that downward force of 6,000. So to re-express that, we have 0.866, negative 0.5, 0, 0.5, 0.866, 0, 0, 0, 1, times 0, negative 6,000, 0. And that's just everything flipped. So we have positive 3,000, negative 5196.150. And now that the relationship between the beam and the coordinate system is the right one, we can draw it however we want. You know, mathematically, all that matters is how the orientation of the beam and the orientation of the coordinate system line up. So now drawing the beam horizontal is the mathematical equivalent of turning your head a little, you know, nothing. So now we can redraw this. The free body diagram has a force vector over here of negative 3,000, positive 5196.15. And a couple of 1,039.23. And then a force vector over on the other end of positive 3,000, negative 5196.15. How many places are there where the subfunction can change? 2. So n equals 2. So 1 cut. And that cut represents all x values between 0 and 0.2. So on the left end, we have the force of negative 3,000, positive 5196.15. A couple of 1,039.23. And then the internal loads, P, V, and M. I left off the torque because there isn't anything happening about the x-axis in this problem. So Newton's second law says negative 3,000, 5196.15 plus T negative V is equal to zeros. So T is equal to positive 3,000. V is equal to positive 5196.15. And the moment equation about the z-axis we have the couple of 1,039.23. The force at the left doesn't produce any moment. Then we have plus m minus Vx is equal to 0. So m is equal to negative 1,039.23 plus Vx, which is negative 1039.23 plus 5196.15x. And then you can do all the checks the same way as you always do. It has to meet all the same requirements. So now you can imagine doing a calculation with some complicated structure. You come up with the external loads on each individual member, and then for each member you apply a rotation matrix that makes the x-axis point along the long axis of the beam. Apply these transformations of those vectors, and then you can figure out the internal loads in each one. I haven't looked at what the assignments are going to be for tomorrow, but so far when we've been doing structures, the structures that we've been calculating have been trusses only, because that's been the stuff that we've been able to calculate the stresses for. When we start doing this, we'll also be doing frames. So the people who took statics from me, you treat it the same way, you know. But if you took statics in a way where you broke things up into trusses and frames, you have to be aware whether you're dealing with only two force members and you can use that truss approximation, or whether there are other loads besides the two forces on the members and you have to use the method of frames. Okay. That's it. We did it.
Could you quickly talk about this